Good morning. Today we are going over our first lecture, and you can find it on the homepage under Exam 1 Materials. But it's the first lecture. It's called Intro Lecture 1 or Introduction to Chemistry. Question: why study chemistry at all? And you guys have to type in the chat here, because there's no point in having a broadcast lecture where there's other people if we don't talk to each other. Why study chemistry? Why are you here, people? It helps us understand what we're made up of, right? It helps us understand ourselves, right? So certainly as health science majors, you guys are particularly interested in the chemistry of the human body, right? But it's more than that, and we will cover that, but it's broader than that. Chemistry is the study of matter. So chemistry, study of matter. That's everything that has mass and takes up space. So that's basically everything, right? Everything. Chemistry studies it, right? What it's made up of and why does it behave the way that it does. And as a result, we kind of consider it to be central to all the other sciences, because any other science, including, say, medicine and pharmacy and biology and nutrition and these other things that are helpful for health science majors, any of these other sciences happens to have matter in them, right? So whether you're talking about the matter that's in that pill for your pharmacy, or the matter that's in that bone for your biology, or the matter that's in that apple for your nutrition class, right? All of those things are things that chemistry can inform us about, right? But it's not just medicine and physiology and nutrition. It's basically everything. So it's going to be geology, because geology is studying rocks, and rocks are matter, right? And it's going to be construction, because construction is going to be using, for instance, concrete, which is a form of matter. And it might be film, because you're developing agents, there's your chemical reaction, and that, whatever thing that you want to fixate it on is kind of matter. It's something that you might not even think of as chemistry, something like music, because as it turns out, if you're making music, usually you're using some sort of an instrument which is made up of matter. And we can talk about how, for instance, the varnish that's used on the wood and the way the wood is treated in the creation of the violin creates a different, richer tone than perhaps a different kind of varnish and a different kind of wood treatment. It's even something like banking and currency, because if you are a government who is printing money for your people, then that money is a thing, and you've got to make sure that you've got a process that will help you print lots of money at a reasonable price, but not allow other people to copy that, right? And so you might be putting special dyes in to your currency, or you might be putting special holograms into your currency, or you might look at the pennies that you're using and realize that they're costing you more than a penny, and so you might take the copper out and put nickel in instead, because as a different kind of matter, it's a cheaper kind of matter. Does that make sense? You guys with me? I'm gonna be like, if you've seen, so if you've seen that movie, I know it's old, it probably dates me, My Big Fat Greek Wedding. There's this point where the Greek father, who is so proud of his Greek heritage, is sitting in the car driving him to school, and he says, "Give me a word, any word, and I will tell you how that word is Greek." Right? So this is me being so proud of chemistry, sitting here saying, "You guys give me a topic, any topic, and I will tell you how that topic is chemistry." It's all chemistry all the way down, guys. I challenge you to give me a to give me a topic where it's not chemistry, right? I love it, Sarah. You're like, okay, something that has no matter and it's just thinking, it's philosophy. But here's the thing, how do we understand ourselves, right? It's philosophy is our brains working, and the way that our brains work is chemistry. And this ends up being a challenge to say, how do we understand ourselves? How do we understand our brains when our brains are the things which are trying to understand them? And is that even going to be possible? But yes, philosophy, that's about the closest you can get, right? to something that might be pure thought and no matter. But because we're thinking with our brains, we're really kind of limited and have to recognize those limitations. Or recognize the fact that there are limitations, even if we can't pin them down, because when you're fish swimming in water, sometimes you don't even recognize the water. There's my philosophical thing for today. So anyways, it's everywhere. It's amazing. And things that you don't think of, you might think, okay, let's think of something really artsy that has nothing to do with science, right? Like if you are totally into 16th century art, you might think that has nothing to do with chemistry until you realize that the process of art restoration and identifying what kind of sources they used for the pigments of that art, that is all chemistry, right? You can tell, for instance, really old pieces of art, if they have really bright, vibrant colors, you know that they used paints that have minerals in them, inorganic minerals. Like a really bright yellow that's lasted a long time, that's got lead in it, guaranteed. But if the colors have faded significantly over time, then you know that the artist used paints which were organic in nature. So something that was like, we crushed up blueberries and we used that for our blue color. That's going to fade over time because those organic materials will oxidize and react with the air and the sunlight over time in ways that the inorganic ones don't. And you might have thought, no, this is not chemistry. I'm interested in the art, but it's there. It's everywhere. Either that or it could be like the Sixth Sense, I guess. I see chemistry everywhere. And that's what I do actually hope by the end of this semester, that you'll start to see it everywhere. You're going to be like my little nerdlets, right? You'll be sitting in, oh gosh, I would say you'd be sitting at a restaurant, but who knows what we're doing anymore. You'll be sitting somewhere with a glass of cold water and the ice in the glass, and you've got condensation on the outside of the glass, and you'll be like, oh, I see heat transfer. The water vapor from the air hit the cold on the side of the glass, and it condensed and it formed water droplets. That's chemistry. It's everywhere, and you're going to be little nerdlets. You're going to be my little nerds, and hopefully it'll be an enjoyable process. And you'll be excited when it happens and not be like, I'm dreaming chemistry and I hate it. But hopefully it'll be exciting. Because I think it's exciting. It is exciting to start to feel like you have an understanding of what's going on in the world around you, and it's not just stuff that happens for seemingly unknowable reasons. And so I find that to be very empowering, right? Even if we don't know all the answers, and it's tempting to think we know all the answers because technology and science have come a long, long, long way. But even if we don't know all the answers, it's just so exciting to be like, yeah, I know what it is that causes that seed to germinate. It's the temperature change that activates, and the combination of the temperature change and the humidity moisture ratio in the soil that causes that thing to go. Or yeah, I know what it is that causes this blood pH level to drop, and I know what to do about that, and I know what it's possible. Anyways, it's empowering, guys. It really is. All right, so chemistry is the study of matter, and it just everything. It's we'll call it the central science. All right, so and we did say what it is. Now has mass and takes up space. So the next question is, how do we know what we're talking about? Right, because I'm going to be talking to you guys about all sorts of things that we actually can't see. The fact is, there's not a microscope that can see an atom. Doesn't exist. Hasn't existed for the last 200 years while people have discovered elements and talked about atoms. So it's kind of crazy for me to be like, yeah, here's what's going on. And you might be excused for saying, yeah, you don't know that. That's crazy. How would you even know that? But the way that we know that is you guys know what I'm talking about. You've got the lecture notes up here with you, right? What is it? I need bigger. How do we know what we're talking about? The scientific method. Okay. Guys, this is not new. I know you have been exposed to the scientific method before. I know you've talked about it before, probably in junior high, if not earlier, right? You guys know generally the order of things here. We are going to talk about it in a little bit more detail. There's more to it. I know it feels like you've done this all your life, so what more could there possibly be? What more could there possibly be? Excuse me. There's, by the way, these, I'm going to put little numbers by here, but it's not like it's this specific thing. I'll guarantee you there's not one scientist that wakes up one day and is like, oh yes, I'm on step 1 of the scientific method today. Right? That doesn't happen, right? But generally you start with something like here. We've got a problem. So you're going to state the problem. Or you might say, make an initial observation. You're observing that there's a problem or a thing. You're like, I found this little roly-poly in my backyard and it's purple. That is really strange. I've never seen a purple one before, right? There's my initial observation. Or you might say, man, I can't get a date to save my life. And I've been crushing on this girl for a long time and I just asked her out and she totally turned me down flat. So that's the problem or the observation, that I can't get a date or that I got turned down here, right? And then we're going to collect data. And when I say collect data, this is just a fancy way of saying I'm going to make additional observations. And maybe those additional observations are going to be in a more controlled environment. So that's how I'm going to call it collecting data. But I'm giving you these examples because I want you to recognize that the scientific method isn't something that like just scientists do. It's like this is a thing that thinking people everywhere do just as a matter of being thinking people, right? That you look at the world around you, and I hope that there are times, several times a day at least, that you might look at something and say, I wonder why that is. That's weird. That's strange. I don't understand it, right? And that on some of those, you might do a follow-up, right, of collecting data. Like you might be curious enough to look for more roly-polies and see if you can find more purple roly-polies in your backyard. Maybe that would help explain why there's purple roly-polies in your backyard. Okay. Or you might sit down and say, all right, here's the number of people I've asked and here's the number of people who've turned me down, or here's what I know about this, these people that I want to go out with that are turning me down. So there's 2 types of observations you can make, and you need to know this terminology. You can make qualitative observations. So these describe a quality, hence the term qualitative. So a kind of quality, oh crap, I didn't mean to do that. For example, like color or state of the matter, right? Those are general qualities. And that is as opposed to quantitative observations. And these are going to describe a quantity, hence the term quantitative. So quantity is something that can be measured mathematically. So math numbers. So if you are measuring mass, temperature, if you are describing the color of that roly-poly, that's a qualitative observation. If you're describing the number of roly-polies or the percentage of those that have a purple color, then that is a quantitative observation. Does that make sense? You guys with me? If you are a COVID-19 researcher trying to develop a vaccine, maybe you're on stage 3 of trials, you're going to test a certain number of people. That's going to be a quantitative observation. You might ask them to describe their feelings qualitatively, or you might give them a survey to say, how are you feeling? Do you feel any fever? Do you feel any weakness? Do you feel any soreness at this point? Do you feel any depression? Do you feel any whatever? And those might be qualitative observations, but then when you aggregate them, you can say, 65% of our COVID-19 vaccination trial patients experienced headaches. Then that's a quantitative observation from the data that you are collecting. All right. Next, once you have some data, and this is kind of initial, then we're going to make a hypothesis. It might feel like your hypothesis is really strong because you've made some observations, but really at this point, what you have is a hypothesis. This is a tentative explanation. Key emphasis on tentative. We don't really know. This is just our guess as to what's happening, right? So your hypothesis might be, this is just a kind of roly-poly, which has a genetic variant that gives them a purple shell. Because I am kind of collecting a number of roly-polies here, and all of these ones in this area of my yard have purple shells, and all the ones in that area of my yard have regular black shells. Everybody know what I mean by roly-polies? I should probably just double check. I always called them potato bugs growing up. They have so many names: potato bugs, pill bugs, roly-polies. Their official name, I looked it up on Wikipedia one day because of course I was curious. Because I made an initial observation that there's so many names and I wanted to know what they were actually called. They're called a woodlouse, which is not a very attractive name at all. I think if I had the name woodlouse, I would petition to have it changed to roly-poly because that's a much cuter name. But anyways, so they're these little potato bugs or pill bugs that roll up into little pills or balls or potatoes if you pick them up. Anyways, and when I moved into my house 10 years ago, I found some purple roly-polies in my backyard. So I'm not making this up. This is a real thing that you could do. Anyways, so you could make a tentative explanation. You might say, I think it's a genetic variant, and that's really interesting. Or you might say, in the case of where you've been shut down, where you keep asking people out on dates, you might say, I think it's because I don't shower enough, and I only shower once a week, and maybe if I shower more often, then somebody will say yes, right? Hypothesis. I collected some data. I noticed that some people were wrinkling their nose. I asked a friend. He gave me some qualitative feedback that my hygiene could use some improvement. So here's my hypothesis. You don't know if that's for sure it. It's just a tentative explanation, all right? And then step 4. And again, I want to emphasize this is not a formal process, right? No scientist is going to wake up and be like, yes, I'm on step 4 of my scientific method today. Today, I'm going to design and administer an experiment. But usually it's just something that thinking people do. And if you happen to be in the sciences, then you might be engaging with, what we would look at as the scientific method on several different levels with multiple different aspects of your problem at any given time. Anyways, but step 4 here, design and administer an experiment. And this is specifically to test the hypothesis. And to test it, what you want to do, if you can, in a different environment, if possible, okay? And the idea, when we say to test it, is we're deliberately trying to get it to fail, okay? So you might say, okay, I think that this is genetic, and so to test it, I am going to crossbreed these roly-polies and see, right? I'm gonna set up several breeding spots, some with purple roly-polies and some with black roly-polies and some together. And I can see across multiple generations, if I have the time and energy to do that, if this is indeed a genetic kind of a thing. And I can predict, is this a 1 or 0? Is it purple or black? Can I get something in between? Is it, 50% is one of these dominant, that kind of a thing. Or I might say, I'm going to start showering 3 times a week, and then in 2 weeks, I'm going to ask this other person out, right? Try again. Just as an idea, right? Again, this is something that real people do all the time, even though they don't call it the scientific method. It's just kind of adapting to your environment, observing your environment and adapting to it the way that you think needs to be adapted, right? Based on your internal hypotheses, essentially. All right, so step 5 here is repeat. Because what happens when you design and administer an experiment is you are going to collect data on that experiment, and that data ends up being an additional observation that comes and climbs into step 2 here, right? Steps 1 and 2. You might make another additional observation when you're doing that roly-poly experiment that all of your purple roly-polies died, right? So there's an interesting observation. Maybe I need to modify my hypothesis now and design a new experiment, right? Now, I'm not going to go back and modify my initial hypothesis and say, this is what I thought would happen, right? That would be dishonest. But it's a circle, right? As you gain more information about the world around you, then you can make more predictions about the world around you, and then you can test those predictions, and then you make more observations, and it just goes around and around. Except if it's just you, then it kind of limits. If it's just you doing it, then it kind of limits what can be learned. But if instead, this is a very important part, very, very important part of the modern scientific method. If instead we do this additional step here, we can invite others to join us on this merry-go-round, okay? And this is how science works today, and you need to be aware of this, all right? Not just as a intellectual curiosity that I'm going to test you on, but like as a human being that lives in the world today, I want you to know how this works, right? So I might run this experiment, I might get this result, I might do it again, I might come up with a model, and I'm going to publish my results. And somebody else is going to come read that paper, right? So what publish it usually means I'm going to write it up kind of formally. I'm going to send it off to a magazine, we'll call it a periodical or a literature. They're going to publish it in the magazine. Somebody else is going to read it, and they're going to say, that's really interesting. I never thought about purple roly-polies before. I'm going to go see if I can find them. And they might look for them in their backyard, and they might run their own experiment. They might repeat what I did. Or they might think of something that I didn't do and repeat that. Or they might say, actually, I haven't done a lot of experiments on woodlouses, but I am a specialist on the woodlouse spider, which, by the way, if you haven't been exploring in your backyards, terrifying looking spider, because it's all like, well, we should probably not talk about it in this class. Anyways, it's not a pleasant looking spider, but it evolved just to prey on the woodlouse. It can kind of punch through its shell, which is kind of cool and also terrifying at the same time. Anyways, somebody else who does research kind of tangentially related to that will see what you've published, and they'll say, I wonder how this affects this thing that I am studying. And so the person who studies the woodlouse spider might get some of these purple and these black roly-polies and do further experiments, and then they might publish their results. And so pretty soon you might have 5-10 researchers doing different experiments around the same problem, and researching and repeating and publishing. And after about 30 years, you get this body of evidence, right? This aggregate of work that helps us understand what is going on here, what the world is really like. And this is a process that takes time. And it's not just because designing an experiment takes time and administering takes time. It's because you have to repeat, you have to publish. If your research is not repeatable, then it doesn't count, right? Then it can't be considered to be true, right? A true description of what's going on. And if it's not published, then nobody else can verify that it's repeatable. So research that isn't published is not particularly helpful either, and we can't know if it's really true, right? So if somebody says, oh yes, I did this thing and this definitely cures cancer, right? Like, unless that is published and other people verify it, I am not going to listen to anything you have to say. I think you're a snake oil salesman, if that makes sense. And it does. It takes a long time. Let me give you a really good example of this. So back in, I need to look this up. There was a study that came out of Canada where a group of researchers looked at mice, and they fed them a diet that was that included a lot of saccharin. Saccharin being the only non-calorie based sweetener that was available at the time. They just added it into their diet. They gave them what we would call a mega dose, because when you're doing research like this, you're really curious what happens if a person drinks a can of diet soda every day. But that kind of research is going to take decades, and so it's a lot faster to try to simulate that by taking something like a mouse and giving them like a megadose. Anyhow, they found that these mice developed bladder cancers at much higher rates than their wild type mouse counterparts. And they published this research, and then the US government was like, well, we have to ban sucralose now, because we have this FDA, it was the FDA said we have to ban it, because Congress has this act that says if there's any substance which causes cancer in any animal or man at any concentration, then it has to be banned. So clearly this one fits that category. And so it was banned. And that was a problem for lots of people. There were a lot of diabetics who were like, well, what the heck am I supposed to use now? And there were a lot of diet and fitness aficionados that were, well, what am I supposed to do now? You can imagine, right? If somebody said that they were going to take away your Diet Coke, or, even if you're not a drinker of Diet Coke, you probably know a lot of people who are very attached to their Diet Coke, right? People are fanatical about their diet drinks. But this was a problem. So, and you might have heard, somebody might have told you, oh, that causes cancer. That's probably referring to this thing. Well, it caused an uproar, but at the same time, you do what you got to do. At the same time, there were a couple of other 0-calorie sweeteners that came on the market shortly after, like aspartame came on shortly after that. So it kind of crisis averted there. But over the next 30 years, there was a lot of research done on this problem of mice and sucralose. And sorry, not sucralose. I think it's sucralose. I think it's sucralose. Anyways, what they found over 30 years, because it takes time, was that yes, it was true. Mice do get these increased bladder lesions, and the reason is that this sweetener would form a complex with a compound that was naturally found in the urine of mice. And those complexes would crystallize out, and those crystals would form on the inside of the bladder and rub on the inside of the bladder and cause kind of lesions, which then made them more likely to get cancer at that point. And then further, they found that humans don't have that compound, and that there's no evidence of crystals, there's no evidence of bladder lesions, there's no evidence of increased cancer rates, which was not terribly surprising, because this particular 0-calorie sweetener had actually been on the market since the 1800s, and nobody had problems with it before. And so it was the year 2000 when this was finally taken off the FDA's cancer watch list. It was about 30 years. I think it was about 1970 when it went on. My dates are all over the place. Sorry, guys. Didn't get much sleep last night. So it was 30 years. By the way, the year 2000 was the first year that cigarette smoke went on the cancer watch list, which Sounds a little ridiculous, but actually it's the first year that they put mixtures on there. Previously, they're like, no, we can only put pure substances on there. And that was the first year they're like, okay, yeah, well, we can say cigarette smoke is a mixture of lots of things that cause cancer. And by the way, we can take this guy off. So that was 30 years of research. And then in 2008, there was another group out of Canada that looked at the same compound, and they took rats and gave them a choice, or they took rats, and on one group of rats, they gave, in addition to their regular diet, they gave them yogurt sweetened with glucose. And on the other group of mice, they gave them the same diet and then additionally supplemented with yogurt that was sweetened with a 0-calorie sweetener. And they found that the mice who had access to the 0-calorie sweetener ended up fatter than those who did not. So it took us, I want you guys to kind of absorb that. It took us 30 years to determine that this is quote unquote safe for consumption. It will not give you cancer. It took us 30 years to determine that. And now we don't even know if it's going to keep us from getting fat, right? Which is the point of taking a 0-calorie sweetener in the first place. Am I right? It's very disappointing to not see your shocked faces on the other side, on the other side of your computers. But your faces should be shocked and confused right now. You should be like, wait, what? It's super crazy, right? So it took us 30 years to determine that it was safe, and now we don't know if it's effective, right? We don't know if it's effective. And so and by effective I mean is effective at giving us something sweet to taste without affecting the bottom line, being like the waistline, basically. All right, so that's the scientific method. And I really want to emphasize this repetition and this publication part, and the fact that it takes time. And that if it's not really an interesting topic, right? Like, who's interested in gut microbiota? Probably a lot of people. But it's still going to take you about 30 years. Now, if it's a world-shattering thing like cold fusion, that's going to be repeated and published. That was within 6 to 8 months. They were pretty sure they knew there was nothing that was there. That's a one for the history books, but you'll see it in your assignment. But that's a world-shattering one that everybody jumped on and tried to replicate instantly, right? Whereas something like sucralose, there's just, maybe 12 researchers working on it. It's going to take time. So when you see a headline in the news that says, coffee causes cancer, a new study came out from so-and-so that says, you can just roll your eyes and nod along and say, great, when I see it's been replicated for 30 years, then maybe I'll stop drinking coffee or whatever, if that makes sense. These are hypotheses. After this has gone through a number of cycles, you can get to the point where you call something a theory. A theory is still just something that they've tested a lot of times and hasn't been found wrong yet. But a lot of people use it as kind of tentatively like, oh, that's just my theory. That's not really appropriate for ones that have been tested for 100 years, right? So you wouldn't say, oh, the atomic theory, that's just a theory. They don't really know if there's atoms. No, we're pretty sure that there's atoms, and you're welcome to try to disprove it. But, there's been a lot of work based on this fact that, and it all works. So we're pretty sure that that's true. Something that you should be aware of. Just going to close with this. There is currently in the scientific community, and this is not a chemistry thing, this is kind of a global thing, concern about a replication crisis, which is to say that maybe up to 50% of the things being published are not replicatable. And if it's not replicatable, what does that mean, guys? Right? If you can't repeat it, then is it true? No, it's not true, which is part of why you're going to wait 30 years, right? You're not going to say, well, this was published in a fancy journal, so it must be true because clearly some scientist has got their work together enough that they can get it published. That's not enough, guys. You have to replicate it. And the replication crisis is there's a number of factors that are feeding into this. But this, again, this is a little bit of this lecture is how does science work in the world today? And I need you to know this because this feeds into things like, you know, when somebody's looking at the COVID-19 vaccines that are on in the market and saying, oh no, they're doing this problem or they're doing that problem. Or when somebody says, you know, hey, we've got this fancy new thing and you should be doing it, you know, and it hasn't, we don't know. Okay, so a couple things that feed into it. Scientists are pushed very hard to do this, right? Most scientists who publish, most of them are currently working as academics in higher education, right? So professors at research level universities then get research funding to do research projects, and then they publish their research. And if they don't have anything to publish, then they don't get tenure, they don't get to stay. So we call it the publish or perish environment, okay? And if you knew that your job was hinged on your ability to publish this kind of material, then that ends up being a temptation for you to maybe fudge the numbers a little bit, right? But this is just one small aspect of it, okay? I don't want you to think that there's like this widespread intentional deception going on, but certainly this attitude is something that feeds into it, okay? Another thing that feeds into it is this thing that you get from journals that you want to publish at, where they say, you know, only interesting things are going to get published, right? If you are managing a magazine, you want lots of people to read it and you're taking submissions on publications, on things to publish. If somebody sends you something really boring, like I did this experiment and it didn't work, you are pretty likely to just be like, okay, well, that's interesting, but I'm not going to publish that because that's not really that interesting to me, right? So what happens is maybe you've got 10 different experimenters running this experiment in the nation, right? And 9 of them get negative results because there's not a result to be had, but one of them gets a positive result because random number generators are random, okay? Sometimes things just randomly happen, right? Let's say, for instance, that you are part of a research team that is studying whether people have ESP skills, right? Yes, is that the right? Gosh, I have to second guess myself. Like, can people close their eyes and see with their mind's eye, right? So you set up this experiment where there's like a black screen between them and somebody else, and that somebody else has some cards that are face up, but the person can't see those cards, and then you ask them to predict what cards they're seeing, right? Something simple like that. You have 10 different people running that experiment, and most of them get no result because it's not a real thing, right? But because some people are lucky, randomly, at least one person out of those 10 is going to get a positive result. And they did the experiment, and they did it right, and they got a positive result, so they're going to publish it. They send that manuscript off to the journal, and the journal says, hey, that's really interesting. You did get a positive result. You weren't even lying, so I'm going to publish that. And then 9 people who get negative results, they're not going to submit their results to the journal because they're not interesting. And so the only thing that gets published was this kind of a one-off, you got lucky, random number generator did its thing, and it's not really a thing. Does that make sense to you guys? You kind of with me? I mean, it's weird that this would give us a result. And it's followed up by something even worse. And that is when this guy reports this result, that he's got some people who can see with their mind's eye, right? Or who can read the mind maybe of the other person that's looking at these cards, right? When somebody reads that and they say, well, I did that and it didn't work, and they try to submit their findings of it not working as a follow-up to say, look, I couldn't replicate it. They submit it to the journal. The journal might say, yeah, but I don't publish negative results, right? And so you can't even refute this wrong thing that was published because the journal is not interested in taking it. So you end up with these, by mistake of nature, that this kind of thing happens. All right. There are other things that feed into it, but you do need to know that this is a thing. In fact, this is a great thing to post on the discussion forums about. You can look it up on Wikipedia. It's called the replication crisis. And you can expect to see it in what we call the soft sciences, like psychology. But actually, it's pretty well documented in medicine. And that should terrify you guys. But it's pretty well documented in medicine. Because, again, you get this thing where your pharmaceutical companies actually are running their own studies, and they don't have to publish them because they're internal, right? And those researchers don't have to publish them to keep their jobs. And so they can run 10 studies, and maybe only one of them gets a positive result, and then they can choose to publish that one positive study and not the 9 that didn't work. And then the pharma reps could take that one study and a bunch of samples around the country to clinics and doctors and say, hey, look, this drug works really well for this thing. Here's our study, this fancy, shiny, peer-reviewed publication that shows that it does. And here's some samples to make sure that you can send it off to your people and see if you get better results. And then, after a couple of years, right about the time that we're discovering through other studies that, these pills don't work any better than the last round of pills, they just cost 100 times more. About that time is about the time that the pharmaceutical company might come out with another new shiny pill that does the same thing, right? Or something different. I'm being maybe a little bit critical of them, but it is true that they'll have internal studies and they don't publish anything that doesn't look good to them. But yeah, so replication crisis it's a real thing. Whether it's 50% of currently published stuff isn't actually true, or whether it's 30%, it's certainly high enough that you should be shocked and concerned, and it certainly is applicable enough to real life. Like we see medicine, we see this in psychology, that you should be skeptical. Always be skeptical. Not necessarily critical, but just be skeptical and look for replication and take time. Because time is what is going to debunk any of those, right? So if somebody's going to come out with something fancy and new, like for instance, the idea of learning styles, and it's going to be such an exciting idea and everybody's going to pile on, and after about 20, 30 years, finally people will admit that it's not a real thing that's going to solve all of our educational problems, and then we can move on to the next fancy shiny thing. Probably growth mindset is the current one in psychology today. Anyways, any questions on the scientific method or the replication crisis? Or this lecture in general? Okay.